There is a kind of silence that exists only in the deepest hours, when the air grows still and the world seems to settle into itself, as if something far below has finally stopped moving, or perhaps has been moving so slowly all along that we simply fail to notice. And in that stillness, if you listen closely enough, you might sense something else, something that has no sound, no motion you could point to, but a presence nonetheless, a weight that has been there longer than memory, longer than mountains, pressing quietly against everything, shaping what cannot be seen. Tonight, we're going to sit with that presence for a while, to follow it downward, not because it demands attention, but because it asks nothing at all. And perhaps that's why it's worth our time. And if this kind of slow, quiet reflection feels like the right place to be, you can subscribe to Quiet Science and continue these journeys with us, drifting through the depths of what the planet does when no one is watching. Beneath your feet, at this very moment, there is a force at work that requires no announcement, no sudden shift, no visible proof of its existence. And yet it has been sculpting the interior of the Earth for billions of years, patient and tireless, a presence so constant that it becomes invisible, like the air itself, like the pull of gravity. Only this force does not pull. It presses, slowly, evenly, endlessly. And the deeper you go, the stronger it becomes, until at some point, the weight becomes so immense that rock itself begins to flow, to change form, to remember what it was made of and what it might still become. And all of this happens in darkness, in silence, without witnesses, as if the planet keeps its most important work hidden, folded into layers we will never touch, performing a kind of alchemy that asks only for time and pressure and the willingness to wait. Pressure, if we're being precise about it, is nothing more than force distributed across space. Weight pressing against surface, molecules crowding together, atoms finding less and less room to exist as they are. But that definition, clinical as it sounds, misses something essential about what pressure actually does, how it behaves. Not as a sudden impact, but as a steady, accumulating presence, the way snow builds on a rooftop through a long winter night, flake by flake, each one weightless on its own, but together creating something that can bend steel, crack timber, reshape what seemed permanent, and all without announcing itself, without any moment you could point to and say, there, that's when it became too much. The air around you right now carries pressure, approximately 14.5 pounds, pressing against every square inch of your skin, your lungs, the surface of your eyes, a weight so evenly distributed, so perfectly balanced, that you've never felt it, not once in your entire life, because pressure reveals itself only through difference, through imbalance, through the moment when one side carries more than the other. Step into an elevator and your ears notice the change. Climb a mountain and your breath grows shallow. Dive beneath the ocean's surface and the water begins to remind you, gently at first, that depth has consequences, that moving downward means accepting more weight with every meter, every foot, every incremental distance between where you are and where you started. But Earth's pressure doesn't wait for you to dive or climb. It's already there, has always been there, building silently in the spaces you'll never visit, the places where rock sits atop rock for miles, where the simple fact of existence means bearing the accumulated weight of everything above. And if you could somehow stand at the base of the continental crust, roughly 20 miles down, you would feel pressure not in the sudden, dramatic way we imagine forces working, but as an all-encompassing compression, something like 3,000 times the pressure at sea level, enough to change the fundamental nature of matter, to make minerals adopt new crystalline structures, to convince rock that it might, given enough time, be capable of flowing like cold honey, inch by inch, century by century, responding to weight the way water responds to gravity, inevitably, without resistance, simply because that's what matter does when pressure asks politely enough and waits long enough for an answer. Scientists measure this in units called pascals, named after a French mathematician who spent his short life thinking about fluids and vacuums and the weight of air. And 1 Pascal is so small, so delicate, that it takes 100,000 of them just to match atmospheric pressure, the baseline condition of standing on Earth's surface and breathing. But go deeper, past the soil and bedrock, past the layers where groundwater still flows and cave systems still hold pockets of open space, down, into the regions where the crust becomes solid and continuous and utterly compressed. And the pascals multiply into the millions, the billions, numbers so large they lose meaning except as a way of saying, this is a place where normal rules bend, where carbon becomes diamond, where the molecular bonds that hold substances together are tested constantly, strained, rearranged, transformed into configurations that simply cannot exist anywhere else. And what's remarkable, what feels almost impossibly subtle when you sit with it long enough, is that this pressure doesn't push in just one direction. It presses from all sides simultaneously, a perfectly uniform compression, as if the Earth were gently squeezing its own interior, not to destroy it, but to hold it in place, to maintain a kind of equilibrium, a balance between the weight pulling downward and the resistance of matter refusing to collapse completely. And somewhere in that tension, in that constant negotiation between gravity and structure, the planet finds its shape, its density, its way of being both solid and dynamic, stable and slowly churning, ancient and continuously changing. There's a thought experiment physicists sometimes use, asking what would happen if you could remove all the pressure from a piece of deep earth rock and bring it instantly to the surface. And the answer is, nothing good. The minerals would destabilize, the crystal structures would fail, the rock itself would fracture or expand or alter its chemistry, not because anything attacked it, not because of heat or force or violence, but simply because pressure, that invisible companion, had been holding it together all along, and without that steady, squeezing presence, the rock wouldn't recognize itself anymore, wouldn't know how to be what it had become, which suggests something about pressure we don't often consider, that it's not just a force acting on matter, but a condition within which matter learns what it can be, a kind of patient instruction, shaping possibility over time frames that make human lifespans look like single heartbeats. And perhaps that's the deeper pattern emerging here, the thing worth noticing as we begin this descent, that pressure doesn't work through moments, through events you could mark on a calendar or capture in a photograph, but through duration itself, through the slow mathematics of weight accumulating across millennia, through the quiet insistence that change, real change, happens not when forces spike suddenly, but when they persist, steadily, without fanfare, until the world beneath our feet has become something entirely different from what it was, and all without anyone noticing, without any sound, without anything we might call drama, just the endless, invisible work of weight bearing down on depth, and depth bearing it in return. Imagine for a moment standing at the bottom of a shallow stream, ankle deep, feeling the gentle weight of water pressing against your shins. Nothing dramatic, barely noticeable, just a slight resistance when you move your legs. A mild awareness that something surrounds you. And now imagine that stream is a mile deep, then 10 miles, then 20. And with each addition of depth, the water above you doesn't change its nature, doesn't become heavier per drop or denser per molecule, but simply multiplies, accumulates, layer upon layer upon layer, until what began as a barely felt presence becomes an encompassing force, not because anything about the water itself transformed, but because there's more of it, endlessly more, stacked vertically in a column that extends upward toward a surface you can no longer see. And that, in its simplest form, is how pressure builds beneath the Earth's crust, not through any special mechanism or extraordinary event, but through the patient arithmetic of depth, the quiet addition of weight that comes from being below instead of above, from carrying the mass of everything that came before. The Earth's outer shell, what geologists call the lithosphere, is built from this kind of layering, though not always in the orderly way we might imagine. Some rocks formed as sediments settling to ancient seafloors, grain by grain, century by century, each particle adding its infinitesimal weight to the growing pile, while others crystallized from cooling magma or were thrust sideways during tectonic collisions, folded and stacked in configurations that seem almost deliberate, as if the planet were carefully arranging its own interior, building archives of time that extend downward in sequences so long and so complex that geologists spend lifetimes trying to read them, trying to understand what each layer means, when it formed, what conditions it recorded. And all of this matters because each layer, regardless of how it got there, adds to the total burden, the cumulative weight pressing down on everything below. Near the surface, where humans drill wells and dig foundations and occasionally tunnel through mountains, the pressure increases gently, almost politely, at a rate of roughly 27 megapascals for every kilometer of depth, a number that sounds abstract until you realize it means that 3 kilometers down, where some of the deepest mines on Earth reach, the pressure has already tripled compared to what you feel standing at sea level, and the rock surrounding those mines, the granite or basalt or ancient metamorphic stone, is bearing that weight continuously, not straining against it exactly, but accommodating it, accepting it the way a strong back accepts a heavy load. And if you were to remove that rock, to excavate it and bring it to the surface, the remaining walls would shift slightly, imperceptibly, as neighboring stone moves inward to fill the space, responding to pressure's redistribution. The way water flows into a void, seeking balance, seeking equilibrium, because pressure, more than anything else, wants to be evenly distributed, wants every point in space to share the burden equally. But 3 kilometers is barely a beginning. The continental crust extends, on average, to depths of 35 kilometers, and beneath ocean basins, where the crust is thinner and younger, it still reaches 7 kilometers down, which means that even at the base of the crust, even at the boundary where rock gives way to the denser, hotter material of the mantle, the pressure has climbed to nearly a gigapascal, a billion pascals, 10,000 times what you're experiencing right now sitting. Wherever you are, and at that depth, at those pressures, rock no longer behaves the way surface rock behaves. It becomes plastic, capable of deforming without breaking, bending over geological time like metal under a hydraulic press, slowly, incrementally, reshaping itself in response to forces that never relent, never ease, never offer a moment of rest. And it's worth pausing here, worth sitting with the realization that all of this pressure, this immense accumulating weight, comes not from any external source, not from something pressing down from above, in the way we usually think of forces, but from the rock itself, from its own mass, its own existence. Every cubic meter of granite weighs roughly 2,700 kilograms, every cubic meter of basalt closer to 3,000, and when you stack those cubic meters vertically for kilometers, for tens of kilometers, the numbers become staggering, the weight almost unimaginable, and yet the rock bears it, has been bearing it for millions of years, for hundreds of millions of years, as patient and uncomplaining as stone can be, which is to say perfectly, indefinitely, without any sign of objection. There's a term geologists use for this: lithostatic pressure, the pressure exerted by the weight of overlying rock. And it's a useful term because it captures something essential about how the Earth's interior works. The way pressure at any given depth depends entirely on what sits above, on the total column of material extending upward to the surface. And this means that pressure isn't something imposed from outside the system, but something the system generates within itself, a natural consequence of having mass and being subject to gravity. And the deeper you go, the more mass sits above you, the more weight you must support, and there's no escape from this, no way to avoid it except to not be deep, to not exist beneath layers of stone and time, and the slow accumulation of everything the Earth has built or buried or simply allowed to settle. And so, the layering continues, invisible and unwitnessed, as it has for billions of years, new sediments washing into ocean basins, volcanic flows cooling and solidifying, tectonic processes thrusting old seafloors upward into mountain ranges, where they'll eventually erode and be carried back down to the sea, only to begin the cycle again. And through all of this, through every episode of deposition and uplift and burial, pressure adjusts, redistributes, finds its new equilibrium. And the rock, plastic and patient at depth, sharp and brittle near the surface, responds in its own time, which is to say, very slowly, slowly enough that to us it appears not to be responding at all, appears to be doing nothing, when in fact it's doing the only thing it can do, the only thing any material can do when subjected to continuous force. It changes, gradually, inevitably, becoming something it wasn't before, all because of weight, because of depth, because of the simple fact that in a planet with gravity, down means pressure, and pressure means transformation. Rock, we tend to think, is the ultimate symbol of permanence, the thing that doesn't change, doesn't yield, doesn't respond to anything except perhaps the most violent forces, earthquakes, volcanic eruptions, the slow grinding of glaciers. But this is a misunderstanding born from living at human timescales, from observing stone across decades instead of millennia. Because rock, when given enough time and enough pressure, is remarkably willing to accommodate, to compress, to rearrange itself at the level of individual grains and crystals, surrendering space it once occupied, allowing its structure to tighten, to densify, to become something closer, more compact than it was before. And this happens not through any dramatic failure or fracture, but through a kind of patient negotiation between the weight pressing down and the material trying to support it, a conversation conducted so slowly that it appears to us to be silence. When sediment first accumulates, sand grains settling to a riverbed, clay particles drifting down through quiet ocean water, fragments of shell and coral and microscopic organisms collecting on the seafloor, it arrives loose and water-saturated, more empty space than solid material, a jumble of particles resting against one another, but not yet bound, not yet committed to becoming stone. And in those early stages, pressure begins its work almost immediately, because even a thin layer of sediment has weight, and as more layers accumulate above, that weight increases, and the particles below, feeling the burden, start to shift, to rotate, to nestle into more efficient arrangements. Grain sliding past grain, finding positions where they can touch at more points, support more evenly and gradually. Over thousands of years, the loose sediment becomes tighter, denser, the spaces between grains shrinking as water is squeezed out, forced upward through the permeable layers toward the surface, carrying with it dissolved minerals that will later precipitate and cement the grains together, transforming loose sediment into solid rock through a process geologists call lithification, a word that sounds technical, but really just means becoming stone, learning to be permanent. This compaction, this tightening under pressure, is measurable. A layer of mud that might start with 70 or 80% water content can, after burial beneath a few kilometers of additional sediment, compress to half its original thickness. The grains force so close together that porosity drops to 20% or less. And what's striking about this is that no external force is required, no tectonic collision or volcanic intrusion, just the simple, patient weight of burial, the slow addition of layers above, and time, always time, because compaction doesn't happen in days or years, but across spans so long that entire mountain ranges can rise and erode in the interim. And the sediment below, oblivious to all of it, continues its quiet densification, continues yielding space, millimeter by millimeter, until it has given up everything it can give and becomes as tight as that particular arrangement of minerals and pressure will allow. But even after lithification, even after sediment has become stone, pressure continues to work, continues to compress, because rock, contrary to what we might assume, is not incompressible. Apply enough force, wait long enough, and even crystalline structures will adjust. Atoms will shift slightly within their lattices. Bonds will flex and strain, and eventually find new configurations that take up less volume. And this happens throughout the crust. At every depth, a continuous background process of compression that we never see, but that shapes the planet's density profile, the way its mass distributes itself vertically. And geophysicists can measure this, can detect how rock at 10 kilometers depth is slightly denser than the same rock type at 5 kilometers, not because it's made of different minerals, but because those minerals have been squeezed into tighter arrangements, compressed by the weight of everything above. And when you drill cores from great depths and bring them to the surface, the rock sometimes expands slightly, recovering a fraction of the volume it lost, like a held breath finally released. Though most of the compression is permanent, locked into the structure by processes that don't easily reverse. There's a quality to this that feels almost alive. The way rock responds to its environment, adapts to pressure, finds ways to accommodate weight without shattering, and it happens through mechanisms we're only beginning to understand fully. Microfractures that open and close, grain boundaries that slide imperceptibly, crystal defects that migrate through the lattice like slow ripples through water. And all of these small adjustments, multiplied across millions of grains, across cubic kilometers of rock, add up to measurable compression, measurable change, the crust slowly settling into itself, finding denser configurations, and the weight that drives this. The pressure that insists on compaction comes from nowhere else except the rock itself, its own mass, its own willingness to be heavy. And this matters more than it might initially seem, because the way rock compresses, the way it yields to pressure without breaking, determines how the crust behaves mechanically, how it responds to tectonic forces, how easily it can be folded or thrust or subducted, and rocks that have spent millions of years under pressure, that have learned to be compact and tight and dense, behave differently than rocks at the surface, are harder to deform, more brittle at shallow depths where pressure is lower, more plastic and flowable when buried deeply where pressure is high, and geologists spend entire careers trying to understand this relationship, trying to predict how particular rock types will respond to particular pressure conditions, because knowing this tells you how mountains form, how continents collide, how the Earth reshapes itself over geological time. At depths where the crust transitions into the mantle, roughly 30 to 40 kilometers down, depending on location, the pressure reaches levels where even the most rigid minerals start to show what scientists call creep, a slow, continuous deformation that happens without fracturing, rock flowing incrementally under stress. And this isn't melting, isn't the rock becoming liquid, but something stranger, a solid-state flow where crystals rearrange themselves atom by atom, responding to pressure and temperature together, moving in the direction that stress dictates. And the rate of this movement is so slow that you could measure it in millimeters per year or less. But given geological time, given millions of years, it's enough to fold rock layers into impossible curves, to bend granite and basalt as if they were soft clay, to reshape the deep crust into forms that seem to defy everything we think we know about how solid materials behave. And perhaps what's most remarkable, what feels almost impossible to hold in your mind when you really consider it, is that all of this, the compaction, the creep, the slow densification of the crust, happens in darkness, in silence, in places no human will ever visit, and has been happening since the crust first formed, since the first rock solidified from Earth's early molten state, a continuous process of adjustment and compression that requires no observers, no consciousness, no awareness of its own existence, just matter responding to weight. The only way matter can, slowly, inevitably, becoming denser, tighter, closer to the configuration that pressure, given infinite time, would prefer. There's a kind of alchemy that happens in the deep crust, a transformation that requires no fire, no sudden catalyst, no moment of dramatic change, only the sustained application of pressure across time so long that to call it patience seems almost inadequate. And in this slow transformation, minerals that were stable at the surface, that formed under one set of conditions and seemed content in their arrangements, begin to feel the strain of depth, begin to recognize that the world they now inhabit is not the world they were made for, and so they dismantle themselves atom by atom and reassemble into new configurations, new crystal structures better suited to the weight they must endure. And this process, which geologists call metamorphism, happens without melting, without the rock losing its essential solidity, just a quiet rearrangement of internal architecture, as if the stone were learning a new language, adapting to a pressure it cannot escape. Consider shale, that fine-grained sedimentary rock formed from compressed mud, soft enough that you can sometimes break it with your hands, layered and fragile, holding within its structure the memory of ancient lakebeds and ocean floors. When shale is buried deeply, when pressure begins to mount as kilometers of sediment accumulate above, the clay minerals within it, those tiny platy crystals that give shale its characteristic texture, start to reorient themselves, start to rotate in response to the directional stress, aligning perpendicular to the greatest pressure. And this reorientation happens gradually, crystal by crystal, as if each grain were making an individual decision to turn, to face the pressure from a different angle. And as this alignment becomes more complete, as more and more crystals rotate into parallel planes, the shale begins to change, begins to develop a new kind of splitting quality, a tendency to break along those aligned planes rather than randomly. And what emerges is no longer shale but slate, harder, denser, with a smooth cleavage that has been prized for roofing and flooring for centuries. And all of this transformation happens through pressure alone, through the patient insistence of weight. But metamorphism doesn't stop there, doesn't reach some end point and declare itself finished. Apply more pressure, bury the slate even deeper, and new changes begin. Different minerals start to grow, larger crystals that weren't present before, mica flakes that shimmer when light catches them, and the rock develops a foliated texture, bands and streaks where certain minerals have segregated themselves, concentrating into layers as if the pressure were sorting them, organizing them, and what was. Once slate becomes schist, a rock that glitters and bends light, that shows clear evidence of having been worked, shaped, transformed at depth, and you can hold a piece of schist in your hand and read its history, can see in its texture the pressure it experienced, the depth it reached, the duration it spent in conditions far removed from the surface world. The minerals themselves tell the story. Certain crystal structures only form under specific pressure conditions, and geologists have learned to read these minerals like instruments, like natural barometers, recording the exact forces that shape them. So when they find garnets, those deep red crystals that grow in metamorphic rock, they know the pressure reached at least 0.5 gigapascal. And when they find kyanite, a beautiful blue mineral with blade-like crystals, they know the rock experienced even higher pressures, conditions that exist only at depths of 25 kilometers or more. And these minerals, once formed, remain stable even when the rock eventually returns to the surface through erosion or tectonic uplift. So they serve as archives, as geological witnesses to events that happened millions of years ago in darkness and silence, under weights we can barely comprehend. What's particularly striking about metamorphism is how it preserves the essential identity of the rock while completely transforming its character. The shale that becomes slate, that becomes schist, is still, fundamentally, made from the same chemical elements, the same atoms that originally settled as mud on an ancient seafloor. But those atoms have been convinced, through pressure and time, to reorganize, to form different minerals, different structures, different ways of being solid, and nothing was added, nothing was removed, just a rearrangement guided by the simple principle that matter, when subjected to enough pressure, will find the most compact, most stable configuration available to it under those conditions. And that configuration might look nothing like what came before, might split differently, shine differently, resist weathering differently, but it's still the same substance, just adapted, transformed, made suitable for a different environment. And this transformation is happening right now, beneath us, in the deep crust where pressure is high and time moves according to geological rhythms. Rocks are metamorphosing, minerals are recrystallizing, new structures are forming grain by grain, crystal by crystal, and none of it requires observation, requires awareness, requires anything except the continuous presence of pressure and the atomic level willingness of minerals to migrate, to break old bonds and form new ones, to accept that their current arrangement is temporary, conditional, subject to revision if conditions demand it. And conditions, at depth, always demand it, always insist on change, always push matter toward denser, tighter, more pressure-appropriate forms. There's something almost tender in this process, in the way pressure doesn't destroy rock but reshapes it, doesn't break it apart but teaches it new ways to exist. And the metaphor writes itself. That transformation under pressure is not violence but adaptation, not loss but evolution, the rock becoming more itself, more suited to its circumstances, more capable of bearing the weight it must carry. And perhaps that's what makes metamorphism worth contemplating, worth sitting with on a quiet night. The idea that even stone, even the most apparently rigid and unchanging substance we know, is willing to transform, willing to rearrange itself when the conditions require it, willing to become something it wasn't. And all it needs is pressure, time, and the deep darkness where change can happen without witnesses, without applause, without anyone noticing until long after the transformation is complete. And so, the process continues, layer after layer of rock being pulled downward by tectonic processes, being subjected to increasing pressure, responding with increasing metamorphism, moving through stages that have names: greenschist facies, amphibolite facies, granulite facies, each one representing a range of pressure and temperature conditions, each one producing characteristic minerals that geologists can later use to reconstruct the rock's journey through the crust. And the fact that we can do this, can read metamorphic rocks like texts describing their own formation, suggests something profound about how pressure works as a recording medium, how it writes its history into the very structure of stone, leaving evidence that persists long after the pressure itself has been released, long after the rock has returned to the surface and the weight has lifted. Because minerals once formed, remember what made them, carry within their crystal lattices a permanent record of the forces that shaped them, and that record, if you know how to read it, tells a story of transformation that happens slowly, inevitably, in the quiet depths where pressure is patient and time is infinite. Pressure, by its nature, seeks equilibrium, seeks to distribute itself evenly across space, and when it cannot, when one region bears more weight than another, when internal differences accumulate beyond what the system can quietly absorb, something has to move, something has to adjust. And in the Earth's crust, this adjustment takes the form of tectonic motion, plates sliding past one another at rates measured in centimeters per year, a speed so slow it makes glaciers look hasty. And yet this imperceptible movement, driven entirely by pressure differences deep within the planet, is responsible for everything we associate with geological change: the rise of mountains, the opening of ocean basins, the gradual rearrangement of continents across the surface of a sphere that never stops trying to balance itself, never stops responding to the internal forces that refuse to stay still. The lithosphere, that rigid outer shell we've been descending through, isn't a single unbroken sphere, but a collection of plates, pieces that fit together like a puzzle but aren't fixed in place. And beneath these plates lies the asthenosphere, a layer of mantle rock so hot and under such pressure that it behaves almost like a very thick fluid, capable of flowing on timescales of thousands of years. And this flowing mantle, heated from below by the decay of radioactive elements and the residual heat from Earth's formation, creates pressure differences, regions where hot material rises and cooler material sinks. And these differences, these gradients in pressure and temperature, exert forces on the plates above, pushing them, pulling them, encouraging them to move in directions that help the system return toward equilibrium, toward a state where pressure is more evenly distributed, though that state is never quite reached, never quite achieved, because new heat, new pressure, differences are always being generated, always disrupting whatever balance might have been approaching. At divergent boundaries, where plates move apart, the pressure beneath the crust is higher than the pressure at the surface, and this difference drives mantle material upward, filling the gap between separating plates with fresh rock that solidifies as it cools. creating new oceanic crust in a process that happens continuously along mid-ocean ridges, those underwater mountain ranges that circle the planet like seams on a baseball. And what's remarkable is how orderly this process is, how methodical. The plates separate at roughly the same rate year after year. The mantle rises to fill the space at roughly the same volume. The new crust forms with roughly the same composition, all because the pressure driving the system is steady, persistent, not subject to sudden changes or dramatic fluctuations, just a continuous push from below, a response to the simple fact that hot rock wants to rise and cooler rock wants to sink, and pressure, feeling this thermal imbalance, translates it into motion. At convergent boundaries, where plates collide, the dynamics reverse, but the underlying cause remains the same. Pressure-seeking redistribution, seeking a way to accommodate two pieces of lithosphere trying to occupy the same space. And what typically happens is that one plate subducts beneath the other, slides downward into the mantle at angles that seem impossibly steep, given that we're talking about solid rock. But at the pressures and temperatures of the upper mantle, rock becomes plastic, enough to bend, to flex, to descend along curved paths that carry oceanic crust back into the depths from which it came, recycling material that once formed the seafloor, melting it, transforming it, eventually incorporating it back into the mantle where it will circulate for tens of millions of years before perhaps rising again somewhere else, beginning the cycle once more. The force driving this subduction is partially the weight of the plate itself. Old oceanic crust, cooled and densified over millions of years, becomes heavier than the mantle surrounding it, and gravity pulls it downward. But gravity alone isn't sufficient. Wouldn't be enough to overcome the friction, the resistance, the sheer mechanical difficulty of bending a 100-kilometer thick slab of rock and forcing it into the mantle. So pressure assists, pushes from behind where new crust forms at mid-ocean ridges, pulls from below where mantle convection creates regions of lower pressure, and together these forces, working in concert across continental distances and geological time, convince the plate to descend, to surrender its place at the surface and return to depth. And this happens not smoothly but in increments, the plate sticking, slipping, sticking again. Each slip releasing energy that propagates through the crust as seismic waves, reminders that even slow processes, even patient processes, involve resistance, involve the friction of solid surfaces grinding against each other in darkness. And between these extremes, at transform boundaries where plates slide horizontally past one another, pressure again drives the motion, but here the mechanism is subtler, more about accommodating the geometry of plates moving in different directions on a spherical surface. And the pressure isn't pushing directly, but rather maintaining the overall circulation pattern, the global system of plates moving in response to mantle convection, and the transform faults, those strike-slip boundaries where plates scrape past each other, are really just accommodations, adjustments that allow the larger pattern to continue, allow plates to maintain their paths without creating impossible geometric conflicts. And so they slip, slowly, intermittently, building stress when friction holds them in place, releasing it when the pressure finally overcomes resistance. And this cycle repeats, will continue repeating as long as Earth maintains its internal heat, maintains the thermal gradients that drive mantle convection and create the pressure differences that refuse to let the crust stay still. What emerges from all this, what becomes clear when you step back far enough to see the whole system, is that tectonic motion isn't random, isn't chaotic, but deeply organized, driven by pressure responding to heat, by matter trying to redistribute itself according to density, by the planet attempting, always attempting, to reach an equilibrium it can never quite achieve because the heat source won't stop. The radioactive decay continues, the pressure gradients persist, and so the plates keep moving, keep adjusting, keep responding to forces that originate deep within the mantle and propagate upward through the crust as a kind of slow, planetary breathing. An expansion here, a contraction there, the entire surface in constant motion, so gradual that only instruments can detect it. Only GPS receivers tracking positions accurate to millimeters can reveal that yes, The ground is moving, has been moving, will continue moving for billions of years into the future. And in this movement, in this response to internal pressure imbalances, there's a lesson about how large systems self-regulate, how they respond to internal forces without any central coordination, without any intelligence or planning, just matter following the path of least resistance, seeking lower energy states, responding to pressure gradients, the way water responds to elevation differences, inevitably, without choice, without alternatives, and the result is a dynamic equilibrium, a planet, that changes continuously but maintains its essential character, its basic structure, because the forces driving change are balanced by the resistance to change, and somewhere in that balance, in that ongoing negotiation between pressure and stability, Earth finds its way of being both solid and fluid, both permanent and constantly transforming. Beneath the crust, beneath the relatively thin layer we've been exploring where rock compresses and transforms and occasionally breaks, lies the mantle, a region of the Earth that extends nearly 3,000 kilometers downward, accounting for roughly 84% of the planet's volume. And everything about the mantle seems designed to confuse our intuitions about how matter should behave, because it is unquestionably solid. Seismic waves pass through it the way they pass through rock, not the way they pass through liquids. And laboratory experiments confirm that mantle material, even at temperatures exceeding 1,000 degrees Celsius, maintains its crystalline structure, its molecular bonds, its fundamental solidity. And yet this solid mantle flows, moves, circulates in great slow currents that take millions of years to complete a single cycle, rising in some regions, sinking in others, driven by the same forces that move air in the atmosphere or water in the ocean, only operating at speeds so slow they make continental drift look rapid by comparison. The mechanism is convection, that familiar process where heated material rises because it becomes less dense, and cooled material sinks because it becomes more dense, creating a circulation pattern, a loop of movement that transfers heat from depth toward the surface. And this happens in your kitchen when you boil water, happens in the atmosphere every time a storm system forms, happens anywhere. Temperature differences create density differences in a fluid medium, but the mantle isn't fluid in any conventional sense, isn't liquid, isn't flowing the way we normally use that word. And yet convection occurs there nonetheless, happens because rock, when subjected to enough heat and enough pressure and enough time, can deform without fracturing, can creep incrementally through processes that operate at the scale of individual atoms migrating through crystal lattices, grain boundaries sliding past one another at rates measured in micrometers per year. And these infinitesimal movements, multiplied across billions of grains and millions of years, add up to circulation, add up to flow, add up to a mantle that churns like a very thick fluid, even while remaining fundamentally solid. Pressure plays a crucial role in this convection, not by driving it directly. That task belongs primarily to temperature differences and the resulting density variations, but by determining how the rock responds to those driving forces, by setting the rules for how quickly or slowly deformation can occur, and at mantle pressures, which range from roughly 4 gigapascals at the top of the mantle to over 130 gigapascals at the core mantle boundary, the behavior of rock changes. Dramatically, minerals that would be brittle at the surface become plastic, capable of flowing, and the higher the pressure, the more resistant the rock becomes to this flow, the more viscous it becomes in its solid state creep, so that the deep mantle moves even more slowly than the upper mantle, taking perhaps 100 million years to complete a single convective cycle, to rise from the core mantle boundary to the base of the lithosphere and sink back down again. And this slow circulation, this patient churning, is what keeps the planet geologically active, what drives the tectonic processes we observe at the surface, because the mantle's convection creates the pressure differences that push and pull the lithospheric plates, creates regions of upwelling where hot mantle rises and exerts upward pressure on the crust, and regions of downwelling where cooled mantle sinks and pulls adjacent material toward it. And these pressure patterns, maintained continuously by the ongoing convection, are what organize plate motion into coherent patterns, what cause divergent boundaries to form where upwelling occurs and convergent boundaries to form where downwelling occurs. The entire tectonic system ultimately driven by thermal convection in a solid mantle, by the planet's attempt to release its internal heat through the only mechanism available, slow, viscous circulation that operates on timescales so long they seem almost infinite to human perception. The pressure gradient itself increases with depth in a predictable way, adding roughly 300 megapascals for every 100 kilometers you descend into the mantle, which means that by the time you reach 400 kilometers down, a depth that represents the transition between the upper and lower mantle, the pressure has already exceeded 10 gigapascals, 100,000 times atmospheric pressure, and rock at these depths behaves nothing like rock at the surface, has been forced into crystal structures that simply cannot exist under lower pressures. Minerals like wadsleyite and ringwoodite that geologists only discovered by recreating mantle conditions in laboratory presses, squeezing samples to extraordinary pressures while heating them to match mantle temperatures. And these high-pressure minerals, denser and more compact than their low-pressure equivalents, mark the depth zones in the mantle, create boundaries where density changes abruptly because mineral structures change, and these boundaries, detectable through seismic studies, tell us something profound about how pressure reorganizes matter, how it forces atoms into tighter packing arrangements, into configurations that wouldn't be stable anywhere except at great depth. And yet, for all its strangeness, for all the exotic pressures and temperatures and mineral phases, the mantle's convection follows the same basic patterns as any convecting system, the same patterns you'd see in a pot of honey slowly heated from below, only stretched across planetary scales and geological time. Hot material rising in plumes, cooler material descending in sheets, the circulation organized into cells that span thousands of kilometers horizontally and extend through the entire depth of the mantle. And we know this is happening not because we've witnessed it directly. The mantle remains forever hidden, forever inaccessible, except through indirect evidence, but because the surface effects are unmistakable, because the distribution of volcanoes and mid-ocean ridges and subduction zones all make sense when viewed as the surface expression of deep mantle convection, as pressure patterns propagating upward from the churning interior. There's something hypnotic in contemplating this movement, in trying to imagine rock flowing like cold honey, in thinking about timescales where 1,000 years of motion amounts to a few meters of displacement, where mountains rise and erode completely in the time it takes mantle material to complete half a convection cycle, and the pressure that enables this flow, that makes it possible for solid rock to circulate, is both the cause and the consequence. Cause because pressure determines viscosity, determines how easily rock can deform, and consequence because the flow itself creates pressure variations, regions of compression where upwelling material meets resistance, regions of tension where downwelling material pulls away from surrounding rock, and these pressure patterns feed back into the flow, influence its geometry, help determine where plumes will rise and where sheets will sink. And so the mantle convects, has been convecting since Earth's crust first solidified 4 billion years ago, will continue convecting until the planet's internal heat finally dissipates, until radioactive decay can no longer generate enough warmth to drive circulation. And even then, even in that far future when Earth has cooled completely, the pressure will remain, will still be present at every depth, still compress rock into dense forms, still maintain the planet's internal structure. Because pressure doesn't require heat, doesn't require motion, only requires mass and gravity, only requires the simple fact that when you stack matter vertically, the material at the bottom must support everything above. And that support, that bearing of weight, is what we've been calling pressure all along. The invisible force that shapes planets from within, slowly, patiently, without drama, without witnesses, without anything except time and the willingness of matter to yield. Pressure, for all its quiet persistence, is not merely a compressive force, not simply a weight that squeezes and densifies. It is also, under the right circumstances, a creator, a maker of substances that could never form in the shallow regions where pressures are low and atoms have more freedom. And nowhere is this creative capacity more apparent than in the formation of certain minerals, rare and precious substances that require not just heat or chemical reactions, but the sustained application of extraordinary pressure, the kind that exists only at depths where the weight of overlying rock has become so immense that carbon, that ubiquitous element, that building block of life and soot and graphite pencils, has no choice but to rearrange itself into the densest, most compact crystalline form available to it. And what emerges from this transformation, what pressure creates in the darkness more than 150 kilometers beneath the surface, is diamond, that hardest, of natural materials, formed not through violence, but through patience, through the slow insistence that atoms occupy less space, bond more tightly, become something they weren't before. Carbon exists in many forms at the surface. Graphite, where atoms arrange themselves in loosely connected sheets that slide past one another easily, making the material soft and slippery, useful for lubrication, for marking paper with pencils, for any application where you want atoms to separate without much resistance. But take that same carbon, subject it to pressures exceeding 5 gigapascals, maintain temperatures around 1500 degrees Celsius, and wait for time frames measured in millions or even billions of years, and the carbon atoms, feeling the weight of 100 kilometers of rock pressing down from above, begin to reorganize, begin to form tetrahedral bonds in 3 dimensions, each atom connecting to 4 neighbors in a perfectly symmetrical arrangement. And this new structure, this diamond lattice, is so strong, so resistant to deformation, that once formed it persists even when brought to the surface, even when the pressure that created it has been released. Because the bonds, once established, are stable, require enormous energy to break, and so the diamond remains a fossil of deep earth conditions, a crystal testimony to what pressure can accomplish when given enough time and enough depth. But diamonds form only in specific regions of the mantle, in areas where the pressure-temperature conditions fall within what geologists call the diamond stability field, a narrow range of depths roughly between 150 and 200 kilometers down, where it's hot enough for carbon atoms to migrate and reorganize, but not so hot that they would rather remain as graphite or dissolve into mantle fluids. And this means diamonds don't form everywhere, don't precipitate continuously throughout the mantle, but only in particular zones, particular depths, and even there they form slowly, crystal by crystal, carbon atoms finding their way to growing diamond faces, adding themselves to the lattice one at a time. And a diamond that's a centimeter across might have taken hundreds of millions of years to grow, layer by infinitesimal layer, in darkness and silence, shaped entirely by pressure and the atomic level tendency of carbon to seek its most compact arrangement under those conditions. And what's remarkable is that diamonds sometimes make it to the surface intact, not through slow uplift and erosion, which would expose them to conditions where they're no longer stable and might revert to graphite, but through violent volcanic eruptions that originate in the deep mantle and punch through the crust so quickly that the diamonds are carried upward faster than they can transform, transported in a matter of hours or days from depths where pressure is immense to the surface, where pressure is atmospheric. And these eruptions, called kimberlite eruptions after the South African town where they were first studied extensively, are rare and ancient. Most kimberlite pipes are billions of years old, relics of early Earth when volcanic activity was more vigorous, but they serve as elevators, as express routes from the diamond stability zone to the surface. And when we find diamonds in kimberlite deposits, we're essentially finding minerals that were created under pressures we can barely recreate in laboratories, minerals that exist only because pressure, at certain depths, insists on particular crystal structures and provides the time necessary for those structures to form. Other minerals too owe their existence to pressure, substances that form only at depths where the weight of rock creates conditions unavailable anywhere else. Stishovite, a form of quartz that requires pressures above 9 gigapascals, formed only in meteorite impact sites or in subducting slabs deep in the mantle, where its presence tells geologists that yes, this rock experienced extraordinary compression, experienced conditions that don't exist in the crust. or coesite, another high-pressure silica polymorph that forms at slightly lower pressures but still indicates deep burial, deep metamorphism. And these minerals, when found in mountain belts, in rocks that were once at the surface, then subducted to great depths, then returned to the surface through tectonic processes, serve as breadcrumbs, as evidence of the journey the rock took, the pressures it experienced, the depths it reached before being exhumed. And geologists can reconstruct entire pressure-temperature-time paths by analyzing which high-pressure minerals are present, which ones have broken down during ascent, which ones remain stable enough to survive the trip back to the surface. There's a quality to these pressure-formed minerals that feels almost magical, the idea that certain substances simply cannot exist except under conditions of extreme compression, that they require the weight of 100 kilometers of rock to stabilize, to form, to persist. And this suggests something about the relationship between structure and environment, about how matter adapts not just through temperature or chemistry, but through mechanical stress, through the simple fact of being pressed upon. And the minerals that form at high pressure are denser, more compact, often harder than their low-pressure equivalents, as if pressure teaches atoms to be efficient, to waste no space, to bond as tightly as physical laws allow. And in the mantle, far below the depths where diamonds form, even more exotic minerals exist, substances like bridgmanite, which makes up roughly 40% of Earth's volume, but exists only in the lower mantle, where pressures exceed 25 gigapascals, a mineral so common in the deep earth but so rare at the surface that it wasn't officially recognized by mineralogists until 2014, when a sample was found trapped inside a diamond that had ascended from extraordinary depths. And this, bridgmanite, with its complex crystal structure and high density, represents what happens when pressure reaches truly extreme levels, when the weight becomes so great that atoms pack together in arrangements that require three-dimensional computer models to visualize properly, arrangements that couldn't be predicted from theory alone, but had to be discovered through high-pressure experiments, recreating mantle conditions in tiny diamond anvil cells, squeezing samples between diamond faces while measuring their crystal structures with X-rays. And perhaps what all of this reveals, what becomes clear when you consider how pressure creates these minerals, these substances that would never form at the surface, is that the deep earth is not just a compressed version of the shallow earth, not simply familiar rocks made denser, but a genuinely different realm, a place where matter follows different rules, adopts different structures, creates different minerals. And all of this difference, all of this exotic chemistry and crystallography, exists solely because of pressure, because of the weight accumulated across hundreds of kilometers of depth, because of the planet's willingness to be heavy, to bear its own mass, to create through sheer persistence conditions that transform common elements into rare and precious forms. At the very center of the Earth, nearly 6,400 kilometers beneath the surface, lies the core, a sphere of iron and nickel compressed to densities that strain comprehension, where pressure reaches levels so extreme that the material behaves in ways we still don't fully understand, where the weight of the entire planet presses inward from all directions simultaneously, creating not just compression, but a kind of symmetrical squeeze that leaves no escape, no direction, that offers relief. And in this innermost region, this final depth, pressure achieves its most complete expression, its fullest demonstration of what sustained weight can accomplish when applied across geological time to the heaviest elements the planet contains. And what exists there, in that compressed sphere, is matter transformed so thoroughly by pressure that it barely resembles the substances we know from the surface. Iron that flows in the outer core, like liquid metal, but crystallizes in the inner core into structures that require the word solid to be redefined, to be stretched beyond its usual meaning. The journey to the core takes you through the entire mantle, through all those thousands of kilometers where pressure steadily increases, where minerals transform and rock learns to flow. But at the core mantle boundary, roughly 2,900 kilometers down, something changes. The composition shifts from silicate minerals to metallic iron. And with that shift comes a dramatic increase in density, from roughly 5 grams per cubic centimeter in the lower mantle to nearly 10 grams per cubic centimeter in the outer core. And this density change is detectable through seismic waves, which slow down when passing from mantle to core, bend at the boundary, create shadow zones where certain waves cannot reach because they've been refracted or blocked by the change in material properties. And these shadow zones, these blank spaces in the seismic record, were how geologists first realized that Earth has a distinct core, a central region fundamentally different from everything above. The pressure at this boundary, where mantle meets core, exceeds 130 gigapascals, more than 1,000,000 times atmospheric pressure. And at this depth, the weight pressing down from above equals the weight of roughly 1,300 kilometers of solid rock stacked vertically, which is already difficult to conceptualize, already pushes against the limits of what numbers can convey. But this is only the beginning of the core, only the outermost edge, and as you descend through the liquid outer core, through that 2,000-kilometer thick shell of molten iron that circulates and generates Earth's magnetic field through its motion, the pressure continues to climb, adding roughly 10 gigapascals for every 100 kilometers of depth, climbing steadily, inexorably, until at the boundary between outer and inner core, 5,200 kilometers from the surface, it reaches 330 gigapascals. And here, at these pressures, something remarkable happens. The iron, despite being at temperatures that would normally keep it molten, begins to freeze, begins to crystallize. Not because it's cooling, but because pressure, that relentless compressive force, finally overcomes the thermal motion of atoms and forces them into a solid lattice, into an ordered arrangement that persists despite the heat, because the weight, the sheer accumulated weight of everything above, leaves no alternative. This inner core, this solid sphere of iron, roughly 1,200 kilometers in radius, exists in a state that has no analog at the surface, no equivalent we can point to and say, it's like this. The pressure at its center approaches 360 gigapascals. The temperature exceeds 5,000 degrees Celsius, hotter than the surface of the sun. And yet the iron remains solid because pressure at these levels constrains atomic motion so severely that even thermal energy cannot overcome it, cannot provide enough vibration to break the crystal structure. And so the atoms remain locked in place, oscillating within their lattice positions, but unable to flow, unable to migrate, frozen not by cold, but by compression, by weight so immense that it redefines what solid means, what stability means, what it means for matter to resist change. The structure of this solid iron, the particular crystalline arrangement it adopts under core conditions, remains uncertain. Scientists debate whether it forms hexagonal close-packed structures or body-centered cubic arrangements, whether the crystals align with Earth's rotation axis or orient randomly, whether the inner core is uniform or contains layers, gradients, variations in composition or structure. And these uncertainties exist because we cannot sample the core directly, cannot retrieve material from that depth, cannot recreate core conditions in laboratories with sufficient precision and duration to settle the questions definitively. And so the inner core remains mysterious, known only through seismic waves, through the way those waves travel through it, reflect from its boundaries, reveal through their travel times and polarizations something about the material they pass through. And from these indirect observations, from this reading of shadows and echoes, geologists construct models, hypotheses, educated guesses about what exists at the very center of the planet. But what we do know, what the seismic data confirms beyond doubt, is that pressure at the core is not just high, but symmetrically high, pressing inward from all directions with equal force, which means the iron there experiences no shear stress, no directional component, only hydrostatic compression, only the pure squeeze of weight distributed evenly across every surface. And this creates a kind of perfect compression, a state where matter is forced to occupy the minimum volume possible while maintaining its atomic identity, where electrons are pushed closer to nuclei, where the spaces between atoms shrink to dimensions that challenge our intuitions about solid matter, because we tend to think of solids as mostly empty space, as atoms separated by distances large compared to their size. But in the inner core, that space has been compressed to near elimination. Atoms pressed so close together that the material's density exceeds 13 grams per cubic centimeter. Iron packed so tightly that a cubic meter of inner core material would weigh more than 13,000 kilograms, more than 13 metric tons. And this density, this compaction, exists purely because of pressure, because of gravitational attraction integrated across planetary dimensions. Because when you gather enough mass in one place and let gravity work on it for billions of years, the center has no choice but to compress, to densify, to become something that wouldn't be possible at any smaller scale. And there's a feedback in this, a self-reinforcing quality, because the denser the core becomes, the more mass it concentrates in a small volume, and the more mass it concentrates, the stronger its gravitational pull, and the stronger the pull, the more the material compresses. And so the core maintains itself, sustains its own compression through its accumulated mass, through gravity acting on density acting on gravity, a loop that has been running since Earth's formation, since the iron first separated from lighter silicates and sank to the center during the planet's molten youth, and will continue running until gravity itself weakens, which is to say, indefinitely, eternally, for as long as Earth exists as a coherent body. And perhaps what's most striking about the core, what makes it worth contemplating on a quiet night when you're trying to understand pressure's full capacity, is that it represents the ultimate limit, the deepest possible expression of what weight can do when given planetary dimensions and geological time. You cannot compress matter more than this without exotic physics entering the picture, without electron degeneracy pressure or neutron star densities, without moving beyond planets into stellar remnants. And so, the core stands as a kind of natural maximum, the heaviest, densest, most compressed state that ordinary matter achieves in ordinary planetary bodies, and it exists down there, unreachable and hidden, bearing the weight of the entire planet without complaint, without yielding, maintaining its structure through pressure alone, through the simple fact that all the rock and mantle above have to press on something, and what they press on, finally, after all those thousands of kilometers of descent, is this sphere of iron, this dense heart compressed to its absolute limit, holding the center. But pressure doesn't limit itself to the solid Earth, doesn't confine its influence to rock and mineral and iron core. It works with equal patience in the ocean, in that vast body of water covering 70% of the planet's surface. And though we tend to think of water as light, as fluid, as something that flows easily and responds instantly to any force, water too has mass, has weight, and when you stack it vertically, when you allow it to accumulate in ocean basins that reach depths of 11 kilometers in the deepest trenches, that weight becomes substantial, becomes a force that presses down with the same steady insistence as overlying rock, creating at the ocean floor pressures sufficient to crush steel, to compress air into liquid, to test the limits of what life can endure. And yet organisms exist there, have adapted to those pressures, have learned to thrive in darkness under weights that would destroy anything built for the surface, which tells us something about adaptation, about resilience, about how life, like minerals, finds ways to accommodate whatever conditions it encounters. At the ocean surface, the pressure is simply atmospheric, the same 14.5 pounds per square inch we experience on land, the baseline from which everything else is measured, but descend just 10 meters, just 30 feet, and the pressure has already doubled. The water above you, that 10-meter column, adds another atmosphere of pressure, another 14.5 pounds per square inch, and this relationship is linear, perfectly proportional, so that every 10 meters of depth adds 1 atmosphere, every 100 meters adds 10 atmospheres, and by the time you reach 1,000 meters, what oceanographers call the bathe epelagic zone, the deep sea, you're experiencing 100 atmospheres of pressure, roughly 10 megapascals, enough to compress air tanks, to squeeze neoprene wetsuits to fraction of their surface thickness, to make every material brought from above adjust, densify, respond to the weight of water pressing in from all sides. And this pressure increases smoothly, continuously, with no sudden jumps or discontinuities, just the steady accumulation of water's weight, layer upon layer, each meter of depth adding its contribution. And what's remarkable is how consistent this is, how predictable. Seawater's density varies slightly with temperature and salinity, but these variations are small, and to a first approximation you can calculate the pressure at any depth simply by multiplying depth by density by gravitational acceleration, a straightforward equation that captures centuries of observation, that describes how water's weight translates into force, and this predictability means that oceanographers can know, without measuring directly, exactly what pressure exists at any point in the water column, can calculate it from depth alone, which seems simple, but represents a profound understanding of how fluids behave under gravity, how mass distributes pressure evenly downward. The deepest parts of the ocean, the Hadal zone named after Hades, the Greek underworld, begins at 6,000 meters and extends to the very bottom of the deepest trenches. Places like the Mariana Trench, where the Challenger Deep reaches nearly 11,000 meters, nearly 11 kilometers, a depth so extreme that if you could place Mount Everest at the bottom of this trench, its peak would still be covered by more than 2 kilometers of water, and at these depths, the pressure exceeds 110 megapascals, more than 1,000 atmospheres, a weight so immense that it changes water's properties, makes it slightly denser than surface water, slightly more viscous, and any material brought to these depths must withstand pressures equivalent to having a metric ton pressing on every square centimeter of surface. And yet the water itself seems unaffected, continues flowing, continues supporting life, continues being water, because liquids, unlike gases, are nearly incompressible. Their molecules already packed closely enough that additional pressure produces only minimal volume reduction. But for organisms living at these depths, for the fish and crustaceans and microbes that inhabit the Hadal trenches, pressure isn't something to withstand, but something to incorporate, something to build their biology around. And they do this not through rigid structures that resist compression, that would require energy, would create stress, would eventually fail, but through bodies that maintain internal pressures equal to external pressures, eliminating the pressure difference that causes crushing. And these deep-sea organisms often have no air spaces, no swim bladders or lungs that would collapse. Their tissues saturated with water at the ambient pressure, their proteins and membranes adapted to function under compression, and some even require high pressure to survive, would die if brought to the surface not because of the pressure drop itself, but because their biochemistry, evolved for the abyss, cannot function properly at atmospheric pressure, cannot maintain the molecular configurations necessary for life when the compressive force is removed. There's something profound in this, in the way life accommodates pressure rather than fighting it, accepts the conditions and builds around them rather than trying to maintain an internal environment radically different from the external one. And this strategy, this approach of equalization rather than resistance, works because water, the medium these organisms are made of, is nearly incompressible. So maintaining internal pressure, equal to external pressure, doesn't require compressing their bodies, doesn't require reducing their volume, just requires eliminating air spaces and using proteins that remain stable under compression. And evolution, given hundreds of millions of years, has discovered multiple paths to this adaptation, multiple ways of making biochemistry work in the deep. The descent into these trenches, whether by submersible or by imagining it, feels different from descending through rock, feels more accessible somehow, because we can picture water, can understand fluids, can relate to the medium even if we can't survive its depths, and yet the pressures achieved in the deepest ocean, while less than those in Earth's mantle or core, are still extraordinary by surface standards, still sufficient to transform materials, to compress and alter and test. And there's a parallel here, a connection between the two realms we've been exploring. In both the solid Earth and the ocean depths, pressure increases with depth, increases linearly and predictably, driven by the accumulated weight of everything above. And in both realms, this pressure shapes what can exist. determines which structures are stable, which forms of life are possible, which materials can persist, and the principle is the same whether you're talking about minerals crystallizing in the mantle or fish surviving in the Hadal zone. Adaptation to pressure requires accepting it, working with it, finding the configurations that remain stable under compression, rather than trying to maintain low-pressure forms in high-pressure environments. And standing on the shore, watching waves approach and retreat, it's easy to forget that beneath that moving surface lies a depth where pressure has transformed the environment into something alien, somewhere as remote and challenging as the deep crust. And perhaps that's the lesson worth carrying forward. The realization that pressure creates hidden realms wherever depth accumulates, whether that depth is measured in kilometers of rock or kilometers of water, whether the medium is solid or liquid, whether the pressure comes from stone or sea, because fundamentally it comes from the same source: gravity acting on mass, weight pressing downward, the simple mathematics of accumulation. And the deeper you go in any direction, the more weight you must accept, the more pressure you must accommodate, until at some point the environment becomes unrecognizable, becomes a place where only the most adapted, the most pressure-tolerant forms can exist, and everything else must remain at the surface, must stay where pressures are low and familiar and survivable. Pressure, for all its capacity to compress and transform, to create minerals and drive convection, has another quality that emerges only when you consider the planet as a whole, when you step back and observe how different regions interact, how the crust responds not just to the weight pressing down from above, but to the distribution of that weight, to imbalances, to places where mass accumulates more heavily than elsewhere. And what becomes apparent is that the Earth's outer layers are constantly seeking equilibrium, constantly adjusting to maintain a kind of balance, a state where the pressure at any given depth in the mantle is roughly equal regardless of whether that depth lies beneath an ocean basin or beneath a mountain range. And this pursuit of balance, this tendency toward pressure equilibrium, governs the vertical position of the crust, determines why continents stand higher than ocean floors, why mountain ranges rise kilometers above the surrounding terrain, and why these elevations, despite appearing fixed and permanent, are actually dynamic, slowly adjusting as erosion removes mass or as ice sheets retreat and their weight is lifted. The principle is called isostasy, from Greek words meaning equal standing, and it describes how the lithosphere floats on the denser, more fluid asthenosphere beneath it, much like icebergs float in water, with their height above the surface determined by their thickness and density. A thick iceberg sits deeper in the water, but also extends higher above it, and the same relationship holds for continental crust, which is thicker and less dense than oceanic crust, averaging 35 kilometers. Depth compared to 7, and this greater thickness means continental crust extends deeper into the mantle, displaces more of the dense mantle rock, and therefore floats higher, achieves greater elevation. And this isn't speculation or theory, but observable fact, measurable through gravity surveys that detect how mass distributes itself vertically, through seismic studies that map crustal thickness, through GPS measurements that track minute changes in elevation as the crust continues its slow adjustments. Imagine the lithosphere as a collection of blocks resting on a viscous fluid, each block with different thickness, different density, and each one sinking into the fluid until it reaches a depth where the pressure beneath it matches the pressure beneath neighboring blocks. And this matching of pressure requires that thicker blocks sink deeper, that denser blocks sit lower. And the result is that the tops of the blocks sit at different elevations. The thick, low-density blocks stand tallest, the thin, high-density blocks sit lowest, and everything in between finds its appropriate level. And this is essentially how Earth's crust works, with continental blocks standing high because they're thick and buoyant, oceanic blocks sitting low because they're thin and dense, and the mantle beneath adjusting, flowing very slowly, allowing the crust to find its equilibrium depth, its balanced position. Mountains, then, aren't simply piles of rock stacked on the surface, but are supported from below by deep crustal roots, thick sections of continental crust that extend down into the mantle. And these roots, these downward projections, are necessary for the mountains to achieve their height, because without them, the extra weight of the elevated terrain would push the crust downward until equilibrium was restored at a lower elevation. And this means that Mount Everest, rising nearly 9 kilometers above sea level, is underlain by crust perhaps 70 kilometers thick, more than twice the average continental thickness. And this extra thickness provides the buoyancy necessary to support the mountain's height, allows it to float high on the mantle without sinking, and if you could somehow remove the mountain, could level it through impossibly rapid erosion, the crust beneath would slowly rise, would rebound upward as the weight was lifted, seeking a new equilibrium, a shallower depth, where the pressure beneath matches the pressure beneath regions that weren't uplifted. And this adjustment, this isostatic rebound, actually is happening right now in regions that were covered by ice sheets during the last glacial maximum. Places like Scandinavia and Canada, where ice kilometers thick pressed down on the crust for tens of thousands of years, pushing it deeper into the mantle, depressing the surface. And when the ice melted roughly 10,000 years ago, when that immense weight was removed, the crust began to rise, began to rebound, and it's still rising. Today, still adjusting, lifting at rates of a few millimeters per year, GPS stations measuring the slow ascent as the mantle beneath flows laterally, filling in the space vacated by the rising crust, redistributing material to restore equilibrium. And this process will continue for thousands of years more. We'll keep lifting the land until the pressure distribution is balanced again, until the crust sits at the elevation appropriate for its thickness and density, without the depression caused by ice. The timescales involved reveal something essential about how the mantle responds to changes in load, to additions or removals of mass at the surface. The initial response is relatively quick, geologically speaking, with significant rebound occurring in the first few thousand years after the ice melts. But full equilibrium takes longer, takes tens of thousands of years, because the mantle, despite being capable of flow, is enormously viscous, resists rapid motion, yields only slowly to pressure. Differences. And so the adjustment happens gradually, the land rising incrementally, year after year, century after century. And you can measure this in coastal regions that were once under ice, where ancient shorelines now sit well above sea level, lifted by the ongoing rebound, and these raised beaches, these fossil shorelines, mark previous positions of the coast, creating a staircase of former sea levels ascending away from the ocean, each step representing a different moment in the rebound process, a different stage in the crust's slow return to equilibrium. But isostasy doesn't only apply to large-scale features like continents and mountains. It works at all scales where mass is added or removed, where the load on the crust changes. So when a volcano builds a mountain through successive eruptions, adding thousands of cubic kilometers of rock to the surface, the crust beneath slowly subsinks, adjusts downward to accommodate the new weight, and eventually the volcano sits lower than you'd expect from simply adding up the thickness of lava flows. Because the crust has yielded, has been pushed deeper into the mantle by the extra load, and similarly, when a major river delta builds outward, depositing sediment at its mouth, extending the coastline seaward through the accumulation of transported material, the crust beneath the delta subsides, makes room for the new sediment, allows the river to continue depositing without simply building elevation indefinitely, and this subsidence is why some river deltas contain sediments kilometers thick, far thicker than could accumulate without the crust sinking to accommodate them. And there's a feedback in all of this, a self-regulating quality, because as erosion removes rock from mountains, reducing their weight, the crust beneath rises, bringing deeper rocks closer to the surface where erosion can attack them. And this means mountains can persist longer than you'd expect if you only considered erosion, because as the peaks wear down, the roots rise up, feeding new material into the erosion zone, and only when the roots are gone, when the thick crust that supported the mountains has been thinned to average thickness, do the mountains finally disappear completely, reduced to plains, to low relief terrain that no longer has the crustal thickness to support elevation. And this cycle, This interplay between erosion and isostatic adjustment operates on timescales of tens to hundreds of millions of years, determines how quickly mountain ranges wear down, how long they persist as topographic features. And perhaps what's most striking about isostasy, what makes it worth contemplating as we continue this descent through pressure's domains, is how it reveals that the Earth's surface isn't fixed, isn't carved once and then maintained, but is constantly adjusting, constantly seeking balance in response to changes in load, in mass distribution. And this adjustment happens through pressure, through differences in pressure at depth that drive flow in the mantle, that cause material to move laterally, to redistribute itself until pressure is equalized, and the crust, floating on this slowly circulating mantle, rides along, rises or sinks as necessary, maintains its balance through infinitesimal adjustments that accumulate over geological time into measurable changes in elevation, changes that reshape coastlines, alter drainage patterns, affect where rivers flow and where mountains stand, all because pressure, that invisible force we've been following downward through rock and water, refuses to accept imbalance, refuses to let one region bear more weight than its structure can support, and works tirelessly, patiently, across millions of years to restore equilibrium wherever it's been disturbed. Standing on solid ground, breathing air, moving through your day, you feel nothing of the pressure we've been describing, sense none of the weight that bears down through kilometers of crust, none of the compression that shapes minerals and drives tectonic motion. And this absence of sensation isn't because the pressure doesn't exist or isn't significant, but because your body, like all surface life, evolved in an environment where pressure is constant, where the 14.5 pounds pressing on every square inch of your skin has been there every moment of your existence, never varying enough to register as change, never creating the difference that your nervous system requires to generate awareness. And so you live immersed in pressure the way fish live immersed in water, surrounded by it, penetrated by it, utterly dependent on it, and yet completely unconscious of its presence, except in those rare moments when it changes, when an elevator rises quickly, when an airplane climbs to cruising altitude, when you drive up a mountain road and your ears pop as the pressure drops by a few percent, by a handful of kilopascals, and suddenly, briefly, you notice. Human perception works through contrast, through differences rather than absolutes. You don't feel temperature, you feel temperature change. Don't hear sound but sound variation. Don't see light but patterns of light and darkness. And the same principle applies to pressure, where your body can detect shifts, gradients, alterations in the ambient force, but cannot sense the force itself when it remains steady. And this means that the enormous pressures in the deep earth, the gigapascals and tens of gigapascals that compress rock and create diamonds and drive convection, exist completely outside your perceptual range, not because they're too subtle, but because they're too constant, too evenly distributed, too perfectly balanced to create the imbalances your senses evolved to detect. And without instruments, without tools that measure absolute pressure rather than just changes, you would never know those forces exist, would have no reason to suspect that the ground beneath your feet bears weight that increases with every meter of depth. And even with instruments, even with barometers and pressure gauges and the sophisticated sensors geologists use to study Earth's interior, the pressures we measure at depth are known only indirectly, calculated from seismic wave velocities, inferred from mineral assemblages in rocks that rose from the mantle, estimated from laboratory experiments that recreate deep Earth conditions in tiny sample chambers. And these methods work, produce consistent results, allow us to map pressure profiles through the crust and mantle with reasonable confidence, but they're still indirect, still one step removed from direct measurement, because we cannot go there, cannot send instruments to those depths, cannot place a pressure sensor at the base of the continental crust and read its output. And so our knowledge of deep Earth pressure, for all its scientific rigor, remains somewhat abstract, a number calculated rather than felt, understood intellectually, but never experienced, never made visceral. The disconnect between knowing and feeling, between intellectual understanding and sensory experience, creates a peculiar distance when contemplating geological forces. You can understand that the mantle convects, can accept the evidence, can follow the logic that connects radioactive decay to thermal gradients to density differences to circulation, and yet some part of your mind resists truly believing it, resists accepting that solid rock flows, that continents drift, that mountains rise from the crumpling of crustal blocks, because none of this connects to lived experience, none of it produces sensations you can recognize, and the timescales involved, measured in millions of years, in hundreds of millions of years, are so far beyond human lifespans that they might as well be infinite, might as well be theoretical constructs rather than actual durations. And so geological processes remain somehow unreal despite all the evidence, remain trapped in a category of things you know, but don't quite feel. And perhaps this is why we build the way we build, why we construct foundations and buildings and tunnels as if the ground were truly permanent, truly stable, as if the pressures and forces we've been exploring operate in some other realm, some parallel dimension that doesn't intersect with daily human experience. Because for practical purposes, for the span of a human life or even a human civilization, the ground is stable, the crust isn't moving measurably, the pressure at any given depth isn't changing, and it's only when you extend your perspective across geological time, when you zoom out to scales where millions of years become visible, that the motion appears, the change becomes apparent. The ground reveals itself as dynamic, responsive, shaped continuously by forces that operate too slowly for biological timescales to register. But occasionally, very occasionally, these slow processes accelerate into human time, produce events that happen fast enough for us to perceive directly. An earthquake releases strain that accumulated over centuries or millennia. A volcanic eruption brings mantle material to the surface in hours or days. A landslide demonstrates what gravity and pressure can do when resistance finally fails. And these events, dramatic and often destructive, give us glimpses of the forces that normally work too. Slowly to see, offer brief windows into the ongoing processes that shape the planet, and in their violence, in their sudden energy release, they reveal just how much force has been accumulating quietly, how much pressure has been building without announcement, waiting for the moment when rock can no longer hold, when the weight finally exceeds the strength, when the slow processes that usually operate invisibly suddenly become very visible indeed. Yet even these catastrophic events, these moments when geological forces enter human awareness, represent only tiny adjustments, brief accommodations of pressure differences that would continue building indefinitely if not released. And the earthquakes that level cities, the eruptions that bury towns, are from the Earth's perspective minor stress releases, small corrections to larger patterns, the equivalent of a person shifting position slightly to relieve pressure on a joint. And once the event concludes, once the shaking stops or the lava cools, the slow processes resume. The pressure begins building again. The system returns to its patient, imperceptible work of compression and transformation. And humans, after rebuilding, after mourning, after adjusting to the new landscape, return to their daily experience of a stable, unchanging ground. The brief intrusion of geological time into human time, fading back into invisibility, into the realm of things that happened, but don't feel like they're still happening. And this raises a question worth sitting with, worth contemplating in the quiet hours. How many other forces shape your world invisibly, operate constantly without producing sensations, change things so slowly that you never notice the changing? And pressure, that force we've been following through rock and ocean, that weight accumulating silently beneath your feet, might serve as a reminder that the most significant influences are often the ones you cannot feel, cannot see, cannot detect, except through sustained attention, through deliberate measurement, through choosing to look for what doesn't announce itself. And perhaps that's the deeper lesson emerging from this long exploration. The realization that the world contains processes operating at scales far beyond human perception, forces that shape continents and squeeze diamonds and maintain planetary equilibrium. And these forces ask nothing from you, require no acknowledgement, proceed with perfect indifference to whether you notice them or understand them or even believe in them. And yet they're there, have always been there, will continue being there long after human awareness of them has ceased to exist. Rock, it turns out, has memory, not in any conscious sense, but in the structural sense, in the way that materials record the forces that shaped them, preserve evidence of the pressures they experienced, the temperatures they endured, the deformations they underwent. And this memory persists long after the forces themselves have dissipated, long after the rock has returned to the surface and the weight has been lifted, because the atomic arrangements, the crystal structures, the mineral assemblages that formed under pressure remain stable at lower pressures, remain locked in configurations that only make sense if you understand the conditions under which they formed. And geologists, reading these configurations, can reconstruct the pressure history of a rock, can determine how deep it was buried, how long it stayed there, what path it took on its journey back to the surface. And all of this information is written in the stone itself, encoded in its structure, waiting to be read by anyone who knows the language. The most obvious form of this memory appears in metamorphic minerals, those pressure-formed crystals like garnet and kyanite that only grow under specific conditions, that require minimum pressures to nucleate and develop. And when you find these minerals in a rock exposed at the surface, you know immediately that the rock has a history, has been somewhere else, somewhere deeper, because those minerals cannot form at surface pressures, cannot exist in their current state unless they experienced forces far greater than anything available in the shallow crust. And the specific minerals present, the particular assemblage of species growing together, tells you not just that the rock was metamorphosed, but approximately how deep it went, what temperature and pressure range it experienced. And geologists have mapped these conditions extensively, have created charts showing which minerals coexist, at which pressure-temperature combinations, so that finding, say, omphacite and garnet together, indicates depths exceeding 40 kilometers, conditions typical of subduction zones where oceanic crust descends into the mantle. But the memory goes deeper than simply which minerals are present. It extends to how those minerals grew, the sequence in which they crystallized, the orientations they adopted, and some minerals, particularly garnets, preserve internal records that are almost biographical, almost narrative in their detail, because garnets grow slowly, layer by layer, adding material to their outer surfaces while the interior remains unchanged. And as they grow, they trap tiny inclusions, fragments of other minerals that were present in the rock at that moment. And these inclusions, sealed inside the garnet, are preserved from further metamorphism, protected from the pressures and temperatures that continue to transform the surrounding rock. And so, they remain as fossils, as snapshots of earlier conditions. And by analyzing the chemistry and mineralogy of these inclusions at different depths within a single garnet crystal, geologists can reconstruct the pressure-temperature path the rock followed, can see how conditions changed as the rock descended into a subduction zone, reached peak metamorphism, then rose back toward the surface. The inclusions sometimes form trails, continuous lines of tiny crystals that mark where a fabric, a foliation, existed in the rock when the garnet was growing. And if this fabric later rotated, if the rock was sheared or deformed after the garnet grew, the inclusion trail inside the garnet preserves the old orientation while the fabric outside shows the new one. And by measuring the angle between internal and external fabrics, by analyzing how the pattern changed, geologists can determine how much the rock deformed, how it was twisted and bent during its time at depth. And this kind of detailed structural memory, this preservation of earlier configurations within resistant crystals, allows reconstruction of deformation histories spanning tens of millions of years, allows us to watch, in slow motion, how rocks responded to tectonic forces, how they folded and flowed and recrystallized under conditions we can only recreate in laboratories. Even the fabric itself, the overall texture of metamorphic rock, carries memory. When rocks are subjected to directional pressure, When force is applied more strongly from one direction than others, minerals respond by reorienting, by rotating their crystal axes perpendicular to the maximum compression, and over time, grain by grain, this reorientation becomes pervasive, creates a foliation, a preferred orientation where platy minerals like micas all align parallel to each other. And this alignment is permanent, remains even after the pressure is released, so that the rock splits easily along those planes, shows a grain that reflects the stress field it experienced, and you can hold a piece of schist, run your fingers along its smooth foliation surfaces, and feel in that texture the memory of pressure, the record of forces that acted millions of years ago in darkness and heat, shaping the rock into a form that remembers which direction the greatest weight came from. And there's a chemistry to this memory as well, because pressure affects which elements can substitute for others in crystal structures, affects which chemical reactions can proceed, which mineral transformations are favored, and different minerals incorporate different trace elements depending on pressure. So by analyzing the trace element chemistry of metamorphic minerals, by measuring the ratios of elements that substitute for major components, geologists can estimate not just qualitatively, but quantitatively the pressures those minerals experienced, can calculate that this garnet grew at 2 gigapascals, that this pyroxene formed at 3, that this diamond crystallized at 5 or 6. And these calculations, combined with experimental data on how minerals behave at different pressures, allow construction of pressure-temperature time paths with remarkable precision, with error bars small enough to distinguish between different tectonic scenarios, different subduction angles, different rates of descent and exhumation. The fact that rocks remember, that they carry within their structure a permanent record of the forces that shape them, transforms geology from a science of speculation into a science of reconstruction, allows geologists to read ancient mountain-building events, to identify where continents collided hundreds of millions of years ago, to trace the paths of oceanic slabs as they subducted and released fluids that triggered volcanism. And this reading of geological memory requires patience, requires careful observation, requires bringing rocks into laboratories and measuring their properties with instruments sensitive enough to detect minute variations in chemistry and structure. But the information is there, encoded reliably, waiting to be decoded. And every metamorphic rock, every stone that bears evidence of pressure and temperature beyond what surface conditions allow, is essentially a time capsule, a physical record of deep earth processes, of journeys through the crust and upper mantle, of tectonic forces operating across timescales that make human history look instantaneous. And perhaps what makes this geological memory particularly striking, particularly worth contemplating, is its passivity, its complete lack of intention. Rocks don't try to remember, don't make any effort to preserve their history. They simply respond to conditions as physics and chemistry dictate, forming stable mineral assemblages under whatever pressure and temperature they encounter. And those assemblages, once formed, persist, not because the rock wants to maintain them, but because changing them would require overcoming energy barriers, would require new conditions different enough to make transformation favorable. And in the absence of such conditions, the rock simply remains as it is, carrying its pressure history forward through time, not as conscious memory, but as structural inertia, as the natural tendency of stable configurations to stay stable until something forces them to change. And this suggests something about how the universe preserves information, how history gets written into matter not through recording devices or conscious attention, but through the simple fact that matter adopts configurations appropriate to its environment and maintains those configurations when removed from that environment, becoming in the process a kind of unintentional archive. There's a word we use in everyday language, borrowed from geology, borrowed from physics, adopted into common speech to describe something we feel but cannot quite articulate. Pressure, the sensation of being weighed upon, of carrying something, of feeling compressed by circumstances or expectations or time. And when we say we're under pressure, when we describe feeling squeezed or stressed or unable to find space to breathe, we're reaching for a metaphor that geology makes literal, that the Earth demonstrates physically, and perhaps there's something more than coincidence in this linguistic borrowing. Perhaps the metaphor works because it captures something true about how forces accumulate gradually, invisibly, until they demand response, demand adaptation, demand that you either transform or break. And the choice between those outcomes, between yielding and fracturing, exists not just for rock under kilometers of overburden, but for anything subjected to sustained force over time. Consider how pressure builds in your own experience, not suddenly, not as a single dramatic event you could point to and say that's when it began, but incrementally, gradually, as small additions accumulate, as responsibilities stack like sedimentary layers, as each new obligation, each new demand, each new expectation adds its weight to everything already being carried. And for a while this seems manageable, seems like something you can bear, because each individual addition is small, barely noticeable, just one more thing in a long list of things. But the weight is cumulative. The total burden is the sum of all those small additions, and eventually you reach a point where the pressure feels immense, feels crushing, and you wonder how it got this heavy when you can't identify any single moment when things changed, any specific event that caused the problem, because there was no such moment. It was accumulation. It was the patient arithmetic of addition. It was weight building, silently until it could no longer be ignored. And the response to this pressure, the way organisms and materials and people handle sustained force, follows patterns that might be familiar from everything we've been exploring. Some things compress, become denser, more compact, reorganizing their internal structure to accommodate the weight, becoming in the process harder, more resistant, transformed into something that can bear what it previously couldn't. And this is adaptation. This is metamorphism translated into human terms. The slow adjustment to conditions that initially seemed impossible. The discovery that you can, in fact, carry more than you thought, that the boundaries you believed were fixed are actually negotiable, movable inward through sustained compression. And what emerges is a new configuration, a new arrangement that functions under pressure that would have overwhelmed the previous version. But compression has limits, and not everything that's subjected to pressure responds by adapting. Some materials, some structures, some ways of being simply cannot compress further, cannot yield additional space, cannot reorganize into denser forms. And when pressure continues to increase beyond what these rigid structures can accommodate, they don't transform. They fracture, break suddenly along planes of weakness, release the accumulated stress all at once in failure. And this too has its human analog, the moment when sustained pressure finally exceeds capacity, when the system that's been holding itself together through effort and will and sheer stubborn refusal to break, finally cannot hold any longer. And the fracture, when it comes, often feels sudden, even though it was the culmination of long accumulation, the final addition to a load that had been building for years. The Earth offers both examples: rock that compresses and transforms under pressure, becoming slate and schist and eventually capable of flowing plastically without breaking, and rock that remains brittle, that accumulates strain until it suddenly slips, releasing the pressure as seismic energy, as an earthquake that feels abrupt, but represents the release of stress that built gradually over decades or centuries. And perhaps the lesson, if there is one, is not that one response is better than the other, not that adaptation is always preferable to failure, but that pressure, whether geological or metaphorical, always demands some kind of response, always requires that the system either change or break, and which of those occurs depends not just on the magnitude of pressure, but on the material's properties, on whether it has the capacity to reorganize, to find new configurations that can bear the weight. And there's something worth noticing in how the Earth manages pressure over long timescales, how it maintains equilibrium, not by resisting forces, but by accommodating them, by allowing the crust to float and adjust on the mantle, by permitting slow convection to redistribute internal heat, by enabling rock to flow when pressures become extreme. And this accommodation, This willingness to yield without collapsing, to deform without fragmenting, operates through mechanisms that work only because they're slow, only because the forces build gradually enough that material has time to respond, has opportunity to reorganize atom by atom, grain by grain. And perhaps that's relevant. Perhaps that suggests something about how sustainable responses to pressure require time, require that the rate of force application stays within the range where adaptation is possible, where reorganization can keep pace with compression. But when pressure builds too quickly, when force increases faster than material can adapt, brittle failure becomes inevitable. And the Earth shows this too, shows what happens when tectonic plates stick at their boundaries, accumulating strain that should be released gradually through continuous creep, but instead builds up until friction is overcome and the plates slip suddenly, catastrophically, releasing in seconds the stress that accumulated over years. And this pattern, this alternation, between slow strain accumulation and sudden release, characterizes systems where the response rate cannot match the loading rate, where pressure builds faster than accommodation mechanisms can operate, and the result is episodic failure, cycles of build-up and release that never quite achieve equilibrium, never quite balance the forces in real time. And bringing this back to human scale, to the pressure that accumulates in individual lives, there might be wisdom in noticing how geological systems handle sustained force, not by maintaining rigid structures that eventually fail catastrophically, but by building in mechanisms for continuous small adjustments, for gradual yielding that prevents pressure from building to fracture levels, by recognizing early when load is accumulating and making small adaptations before those adaptations become impossible, before the only available response is brittle failure. And this isn't advice exactly, isn't prescription, because people are not rocks and metaphors have limits, but it's observation, it's pattern recognition, it's noticing that systems which successfully manage pressure over long timescales tend to be systems that remain plastic, that maintain capacity for continuous adjustment, that don't try to resist force absolutely, but instead accommodate it incrementally, finding new equilibria as conditions change rather than defending old configurations that no longer match the environment. And perhaps the deepest connection between geological pressure and human experience isn't in the metaphor of being compressed, of being weighed upon, but in the recognition that transformation under pressure is not failure, but adaptation, that becoming denser, harder, more resistant through compression is a valid response, a way of surviving conditions that would destroy materials that remained unchanged, and the metamorphic rocks we find at the surface, those stones that bear evidence of extraordinary pressure that show in their foliation and their mineral assemblages the forces they endured, are not damaged or broken, but transformed, shaped into forms that could only exist because they experienced what they experienced, because they went deep and came back changed, and they persist not despite their history, but because of it, their structure now suited to surface conditions precisely because they learned, in the deep, how to accommodate force. If you could somehow perceive the Earth entire, could see it not as a static sphere, but as a dynamic system operating across geological time, you would notice something resembling breathing, a slow expansion and contraction, a rhythm of uplift and subsidence, of compression and release, driven entirely by pressure redistributing itself through the planet's interior, seeking equilibrium, but never quite reaching it, because the system is always changing, always responding to new heat from radioactive decay, new weight from accumulating sediment, new adjustments as plates collide or separate. And this planetary breathing operates at frequencies so low, wavelengths so long, that individual cycles span tens of millions of years, are invisible to any observer existing at human timescales. And yet they're there, have been there since the planet formed, will continue until internal heat dissipates completely, and the Earth finally stills, finally stops its slow respiration, and becomes truly static, truly dead in the geological sense. The breath in, the compression phase, happens wherever material descends, wherever weight accumulates, wherever forces push downward, at subduction zones where oceanic plates sink into the mantle, in sedimentary basins where rivers deposit their loads and the crust subsides to accommodate the growing pile, beneath ice sheets where glaciers press down and depress the land, and in all these places pressure increases, weight builds, the crust is pushed deeper into the mantle, and this descent, this compression, stores energy in the system, creates potential that will eventually drive the breath out. The expansion phase, though not immediately, not quickly, because the mantle yields slowly, responds to pressure differences on timescales of thousands or millions of years, and so the compression can continue for long periods before the response begins, before the flow in the mantle catches up and starts to redistribute material, starts to relieve the pressure imbalance. The breath out, the expansion phase, happens wherever material rises, wherever weight is removed, wherever forces push upward, at mid-ocean ridges, where hot mantle wells up to fill the gap between separating plates, in regions experiencing isostatic rebound, where ancient ice sheets have melted and the crust slowly rises, in mountain ranges where erosion removes rock and the roots ascend, seeking new equilibrium. And in all these places pressure decreases, weight lifts, the crust moves toward the surface, and this ascent, this expansion, releases the energy stored during compression, allows the system to return toward balance, though never completely, never finally, because new compression is always starting somewhere else. New weight is always accumulating. New imbalances are always forming, and so the cycle continues, breath following breath, compression following expansion following compression, the planet maintaining itself through continuous adjustment, through perpetual response to internal forces that refuse to equilibrate. And between these phases, between the clear moments of descent and ascent, lies the majority of geological time, the long intervals where pressure builds so gradually that it seems like nothing is happening, where strain accumulates in the crust, where heat diffuses upward through the mantle, where minerals slowly transform in response to their changing environment. And this apparent stillness, this period between breaths, is not inactivity, but preparation, the slow gathering of force that will eventually produce motion, produce change, produce the next phase of the cycle. And perhaps this is the most important part, the part we most often overlook, because the dramatic events, the earthquakes and eruptions, the mountain building episodes and basin formations, are merely the punctuation, the moments when accumulated pressure finally manifests as visible change, while the real work, the sustained force that makes those events possible, operates continuously in the quiet intervals, in the times when the planet seems static but is actually building toward its next adjustment. Pressure then functions as the planet's regulatory system, its way of maintaining dynamic equilibrium, responding to imbalances not instantly, but eventually, not through active control but through passive physical principles. Heavy things sink, light things rise, hot things expand, cold things contract, and pressure differences drive flow that redistributes material until the differences diminish. And this self-regulation requires no intelligence, no intention, no awareness of what the system is doing, only matter responding to forces according to physical laws, only atoms and molecules and mineral grains behaving as they must given their properties and circumstances, and the result is a planet that maintains itself, that adjusts continuously to internal changes, that never reaches final equilibrium, but never departs far from approximate balance. And there's something almost meditative in contemplating this, in thinking about how the Earth manages its internal forces through slow, patient adjustment rather than through resistance or rigidity, how it accommodates change by changing, how it responds to pressure by redistributing it, rather than trying to maintain some fixed configuration against all forces. And this approach, this strategy of continuous accommodation, has kept the planet geologically active for over 4 billion years, has maintained oceans and atmosphere and magnetic field through all that time, has created conditions stable enough for life to emerge and evolve and diversify, and perhaps stability, real stability, across geological timescales, comes not from resistance to change, but from capacity to adjust, not from maintaining fixed states, but from flowing between states as circumstances require. Not from being solid in the sense of rigid, but solid in the sense of coherent, capable of deforming without fragmenting. The rhythm continues beneath us, will continue long after we're gone, pressure building and releasing, material ascending and descending, the crust adjusting its elevation, the mantle circulating in its slow convection, the core maintaining its compression, and all of this happens whether observed or not, whether understood or not, whether believed or not, because geological processes don't require witnesses, don't depend on consciousness, operate according to principles that predate life and will persist after life. And there's something humbling in this, something that puts human concerns in perspective, the recognition that we live on the surface of a planet that has its own processes, its own timescales, its own ways of being that have nothing to do with us, that operated for billions of years before we appeared and will operate for billions more after we're gone. And our presence, for all its significance to us, barely registers at geological scales, barely affects the deep, processes that shape continents and drive plate tectonics and maintain the planet's internal equilibrium. And yet we're part of it, participants whether we acknowledge it or not, subject to the same forces that compress rock and transform minerals, living under the same pressure that exists at the surface, breathing air whose pressure we cannot feel but depend upon completely, standing on crust that floats on mantle according to the same isostatic principles that govern how icebergs float in water. And in that participation, in that unavoidable connection to geological reality, there might be something worth recognizing, worth sitting with, the understanding that pressure, that invisible force we've been following through layers of rock and ocean, through depths we cannot visit, and scales we cannot perceive directly, is not separate from human experience, but continuous with it, not alien, but fundamental, part of the basic physical reality that shapes everything. And so we return to where we began, to the surface, to the quiet hours when the world settles into itself, and the stillness that seemed like absence reveals itself as presence, as the continuous work of forces too patient to announce themselves, too steady to require acknowledgement. And perhaps now, having followed pressure downward through rock and water, through depths where minerals transform and iron compresses, and the planet maintains its slow equilibrium, that stillness feels different, feels less like emptiness and more like the surface expression of everything happening below, the calm face of processes that operate without urgency, without drama, content to work at speeds that make mountains look temporary and human lifespans look like brief flickers of awareness in a much longer darkness. The pressure is still there, has been there through this entire conversation, pressing down through kilometers of crust, accumulating with every meter of depth, shaping rock in ways we cannot see, driving circulation we cannot witness, creating minerals in darkness we cannot penetrate, and it will continue this work long after these words fade, long after the particular configuration of atoms that briefly held consciousness and called itself human has dispersed back into the elements it borrowed, because pressure doesn't care about observers, doesn't require understanding, doesn't need belief or validation, only mass and gravity and time, only the simple fact that when matter accumulates, the bottom must bear the weight of everything above, and in that bearing, in that patient acceptance of load, the planet finds its form, maintains its structure, continues its 4 billion year habit of being solid and dynamic simultaneously, still and constantly changing, permanent and utterly temporary, depending on what timescale you're using to measure. We like to think we understand things, like to believe that knowledge equals mastery, that naming forces and measuring pressures and mapping the interior of the Earth means we've somehow grasped it, brought it under control, made it knowable in the way we make other things knowable. But pressure, in its patient persistence, suggests otherwise, suggests that understanding might be less about control and more about recognition, less about mastering forces and more about acknowledging them, sitting with them, allowing them to exist in their own time, without demanding they explain themselves or justify their presence, or operate according to schedules that make sense to consciousness, that measures duration in heartbeats, rather than the slow drift of continents across the surface of a sphere that never stops adjusting its own weight. There's a kind of peace in this, in recognizing that the world continues its work, whether you understand it or not, that pressure shapes the planet from within, regardless of whether anyone is paying attention, that the forces we've been exploring exist in their own right, serve no purpose beyond simply being what they are, responding to conditions as physics dictates. And in that purposelessness, that complete lack of intention or goal, there's something almost restful, the realization that not everything needs to mean something. Not everything requires interpretation. Some things simply are, simply continue being, simply perform their slow transformations in darkness and silence, without any concern for significance or meaning, or whether their existence serves any larger narrative. The night deepens, the stillness persists, and beneath your feet the pressure continues, building in some places, releasing in others, maintaining the delicate balance that keeps the crust floating on the mantle, keeps the continents standing above the ocean floor, keeps minerals stable in their appropriate zones, keeps the planet breathing its slow geological breath. And this work will continue through tonight, through tomorrow, through all the tomorrows that extend into a future longer than imagination can hold, because that's what pressure does. It persists, it accumulates, it shapes slowly and without announcement, and in its persistence it creates the ground you stand on, the mountains you see, the ocean depths will never visit, the core will never touch, all of it held together not by force, but by weight, not by resistance, but by acceptance, the planet bearing its own mass with a patience that makes eternity look hasty. If this journey brought you a sense of calm, you can subscribe to Quiet Science and continue exploring these silent depths with us.